Welcome, everybody. Tonight, we're going to be working on Unit 9. The primary topic for the evening is designing a database. And you can see at the very top of the unit folder here, it says how to design a database. We'll also talk about this thing called database normalization and relationships that we have between tables. Kind of scroll down here just a little bit and you can look at our topics. Basically, it's not really a topic list necessarily, but it kind of reiterates all that information. Designing a database is a process, by the way, and thus far the work that we've been doing, we've been working with databases that already exist, or we ran scripts that would create them for us and populate them with content and all the tables and all the relationships, and the data is all normalized and all set to go, right? And that's wonderful when you have that. But often the job of a database person is to either build a database from scratch or build a database based upon information that's already on hand. Those are very common tasks. Or maybe even something like, hey, look, we have this stack of paper here. Wouldn't it be nice if it was in the database, right? And go from paper to electronic format. And then when you do design a database, you have to think about like how you're going to build the tables, what information goes in there, how you're going to link them together, what the data structure is, the data types, and all that stuff, that we've been kind of working with. If you do have a copy of our old text, the Murox MySQL 3rd edition, by the way, that this is chapter 10 content, and I do have the old PowerPoint from that down below, and you can visit that if you wish. Notice that I do talk here about the three main types of database relationship types, how we connect tables together. So we'll talk about this one-to-one, one-to-many, and many-to-many relationships. We'll go through the process of normalization. In fact, our homework for this unit is to normalize some raw information. And we'll do examples of how that works, by the way, so that you have a guide. I do have my old lecture video from last fall out there, the PowerPoint. And then what I'm going to do now is I'm going to talk about this entry here, which is database design. And notice I have some information here, and I hope you guys do take the time to read it before you come to class. But if you haven't, and yes, I'm sorry, I'm going to kind of read it back to you. And we're going to talk about some really key concepts here, ones that are very important for database work, but it's not where we start the teaching, because we want to get you into a database and running queries so you get what that feels like, right? And we have a pretty good history of that now, because we've started with really basic queries, if you think back on it. And then we started joining tables together. And then we started, working with functions and data types, and now understand like what a primary key and a foreign key is, and subqueries, and yada, 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 all that stuff that we've been learning. And now, with that in mind, that we know how it functionally works when it's there, now we have kind of enough fuel to think about how we would design a database if we didn't have a database for the thing that we wanted to build it for, right? And this is a different type of task and skill necessarily than just running a query and extracting information. So let's kind of read through the content here. I'm going to click in like a couple clicks on Zoom here so we can see the content a little bit more clearly, kind of like a PowerPoint or something, I guess. And it says a relational database system should model the real world environment where it's used. The job of the designer is to analyze the real world system and then map it into a relational database system. So for example, if I worked in a doctor's office, and this is a really great example because doctors up until very recently, and maybe your doctor still does this, would keep their records on paper. Always. Like you'd go to their office and they'd pull a folder, right? And it's got paper in it, and they write notes on the paper. And now a lot of our big hospital systems and clinics and even private doctors' offices are part of bigger health networks. and they now enter your information directly electronically into their database, right? Like, and if you guys, visit the doctor somewhat regularly, you know what I'm talking about. But when they took the data that you would put in a patient's file and put it into an electronic format, well, I have this real file, right, that represents a real world situation, the doctor's office, the patient, the treatments, all the stats we have on the patient, the medicines, and all that stuff. And the database has to model all the stuff we do in the real world. So, like, if the doctor has a place where they put in notes or observation or test results or patient information or whatever, right? The database also has to have that, so like if we're dealing with certain types of data, we have to have a data construct to hold it. All right, so that's the entire database. Second bullet, a table in a relational database is typically represents an object or an entity in the real world. For example, if I had a database for a doctor's office, I would probably have a patient table, right? And then I might have a test results table, and then I might have a, did you pay your bill table? All of those pieces. So every table, I want to read this again. Every table in a database typically represents an object or an entity in the real world, right? So we have a patient table because that represents patients, and those are real things, right? Or a table for tests or test results because that represents a real thing also. Each column of the table is used to store an attribute associated with the entity, and each row represents one instance of the entity. So, for example, if I have a patient table, well, they're going to have probably a patient ID, the first and the last name, an address, a phone number, etc. Right? These are kind of typical. And then each row in the table represents one instance of the entity. So, for example, one instance might be one patient in the patient table. Or if it's a test results table, it might be the test results for one patient, that type of thing. And this terminology is not accidental. This is all about the design of tabular data, or rows and columns of information. People put a lot of theoretical thought into this, if you can't tell. And databases have been around a very, very long time, as have spreadsheets and what we call table information or tabular information. We have a lot of terms that we kind of use interchangeably, and we'll talk about those terms as well. So third bullet, to model a database and the relationship between its tables after a real world system, you can use a technique called the entity relationship modeling diagram. And it says some of the diagrams you'll see in this chapter apply the basic elements of what we call entity relationship modeling. And here's what's kind of interesting is whenever we're working in a tool like MySQL Workbench, and we can do this in MySQL, by the way, Workbench, and I'll show you just momentarily how to do this. You can connect to a database that already pre-exists, that has data in it and a bunch of tables, and all the relationships are formed. Even if you didn't build it, as long as you have the right access rights, and you can look at the structure, and you'll notice, like, this image here, this is a graphical representation of the tables and the connections between the tables as well. And you can see it graphically. In fact, I'm going to show you how to do this right away in MySQL Workbench. So I do have it open, and I am connected up. And in last week, what we were working on the Guitar Shop database, which is the schema for it is expanded over here, and I realized that you can just come over here, expand the tables, and go, well, this is my database, these are my tables, and then I can look at each table and look at the keys and all, like what stuff is here. But I mean, so I kind of have access to the structure already. I mean, I can tell how many tables there are, what kind of data fields it has, and what the primary key is and all that. What I'm not seeing, though, is how those tables necessarily connect. If I wanted to figure that out, I kind of have to go like, well, let's see, I got a customer and he's got a customer ID, and then I got orders. Well, that's got a customer ID, so this customer ID must match up with that customer ID, that kind of thing. And that's kind of cumbersome. And I could, but I could kind of by hand draw a representation basically containing all this table information here, and then like draw lines between it. And I can do that manually. And I could use a graphics program, for example, to do it. Now, what's kind of neat about a tool like this, being a high level database management tool, is if you go to the database menu up here at the top, they do have this command, and we're going to revisit this command, by the way, even more next week. But you can trigger the reverse engineer menu option here, and I'm just going to bring this up on the screen and show you how it operates. So you get this dialog box, and you'll notice in the background what happened is it opened up a tab that shows the MySQL model. So it shows you kind of like I guess like the rudiment structure of a database. But right now, it doesn't know which database we're attaching to, right? But in the background, we could work with it in principle. So I could create a new database from that interface and tables and all that. All right. So this dialog box comes up, and what it's asking right off the bat is, which database system are you connecting to? Well, my local one. That's the one that we're running. So it's looping back through TCP/IP on my own system. But I will tell you, like, for example, the student that was here getting help right before class started, he was having issues connecting to our remote database on Prometheus with his Java program. And so instead of it being a local database, it could be a remote one. So instead of it saying local host here, it could say an IP address that's numeric, or a host name that's words, like our school server is prometheus.gtc.edu. And then you would have to know the correct host name and the port number, and once again the username and the password to connect to it. Now these are already stored in here, so I don't have to change them, and I'm looping back to my own machine, right? So MySQL is running in the background. So I'm going to go to the next screen, and then it says, okay, connect to the database and fetch information, retrieve the schema list from the database, check the server configuration issues, and apparently there are none, and it looks like it worked, right? So it looped back to the server, logged in, grabbed all the information from the database that I need to make this diagram, and it's kind of ready to build it now. And it says, select the schemas you want to include. So which database do I want to look at? Well, I don't want to look at all of them. I just want to focus on one. So let's just make it really simple. I'm just going to choose My Guitar Shop, right? And then I'm going to go ahead and click Next. All right. It retrieved the objects from the selected schemas, and it checked the results, and it says successful. We're going to move on to the next screen. All right. It's going to import the table objects. So it recognizes there's 7 tables. So it's going to do that. Now it's going to execute. And then in the background, right, and this step is basically done here. We're going to click Next and then click Finish. And then when we're done, we can see a diagram of all the tables in the database and their connections. And notice how graphical it is. Now, some of the way that it lays this out is it kind of goes through them sequentially, puts images on the screen. And if you look at each one of these images, right, you'll notice the name of the table, all the fields are listed with their data types, and it shows you which ones are primary keys, etc. And that kind of continues. And notice I have one table called administrators that I don't necessarily see in the schemas, but this just holds the username and passwords of the admins of the database, right? So it's not really part of the data part of the database. The other neat thing is you notice as I hover over a table, and you notice like the blue field lights up, so the primary key, and it shows you that it links from this table to up here. So the order ID, the blue one, links through this connection to this table up here. And you see how they both highlight blue, and then the other one highlights green, and that connects to that other table. But notice like the line goes over and down and under and behind another table. It kind of makes it a little hard to see, honestly. Well, here's the neat thing is these are all drag and drop pieces. And this is kind of neat, right? So like I can take, for example, let's say my customers table and move it here, and I can move my categories over there. Maybe my addresses can go here, right? And what I'm really trying to do, if you're not like figuring it out, is I'm moving the stuff so that I can see, kind of like eliminate some of the overlaps, right? So I'm not like kind of stepping on something else to figure out where the pathways are. So this is clearer to me, right? And hopefully you agree. You notice how the administrators table is linked to nothing because this just holds usernames and passwords. It is not connected to the data relative to our customers, our orders, our inventory, none of that, right? That's just the username password database that sits separate. However, all the other tables are connected, right? And they're connected in the ways that we were mentioning. The blue lines, right, show that that primary key field is a foreign key. So like from the products table, product ID is a foreign key in order items, and they both highlight blue, right? And the green one, once again, is a foreign key from the categories table where it's a primary key. And then if you notice really, really carefully, on these lines, right? And you see when I hover over them here, it shows you that like how they connect, which fields are the connection points. And those colored connections are the relationships. So when we have tables of information and we call it a relational database, it is those connections that make it a relational database, right? Why do we split stuff into tables? Because it's more data efficient. We've talked about that already, but we're going to like reinforce it now that we're learning about normalization, basically. The other thing that's here, and this is a little harder to see with the graphics, but you'll notice that there's these little symbols here, and they have a meaning, and these are not very clear. And I don't know if I can zoom in here. Let's see if we can zoom in a little bit. Oh, it's not letting me, and I'm not sure how, so I don't want to mess with it right now because it looks pretty good on the screen. But you'll notice that there's these connection things here, right? And you'll notice that they have this like nomenclature of these different terminologies. And basically, for example, if I have one customer, my one customer might have many orders. So really what these symbols here mean is one, this little like hash, the two slashes through it means one to many. So we take one customer that might have many orders, right? And then one order might have many order items, right? And you see the same connection type. In fact, most of the connections here are one to many. In fact, I think all of them are one to many. They all are one to many. Sometimes, so for example, if I kept my customer information, for example, let's say I kept my customer ID in a separate table from my customer demographics, that might be a one-to-one relationship. So for every entry in the table, it has only one entry in a different table. Sometimes I can have many entries in a table connecting to many other entries in a different table, and thus kind of all this terminology. When you look back in the core shell here too, and we start to talk about it one-to-one, one to many, and then when it's many to many, we use M and N for some reason instead of M and M. I don't understand why, but there's a reason for it. All right, so this process is actually pretty helpful because like if you were working with a big, large, complex database and you weren't clear what the connection points are, like how the data is structured, that reverse engineer feature is very, very helpful. I mean, you can visually see how the tables connect together, and in one screen, I can see all the tables, all the columns for each table, the keys, the data types, the connections, and all of that. Right? It's all present here. These things can be, in some cases, altered. Right? So you can actually use the little glyphs here to kind of change things and what we're seeing on the screen. Um, and I would be really cautious about changing anything that's working, by the way. You'll also notice that some of the tables have indexes and they're indicated here. So like, for example, the customer table has two indexes, one for the primary key and one for the email address. And it looks like all the tables are indexed here, and you can go through and look at them. Typically, at a minimum, your primary key is always indexed. That's kind of normal. And I'll have you think about this, right? It kind of has to be in order for it to be unique. In other cases, though, and I don't know, the customer table, like if I was doing a database, all right, I get the primary key and an index off the email address, but I might also create a index by last name, or maybe an index by country or something like that, to further sort the information. And we'll talk about how indexes work and all that and how to create them coming up. But that information is available here as well. You can also, if you have a ton of tables, right? So like you can also collapse the tables down and only expand them when you need to. So you can put a whole bunch of stuff on the screen real concisely. But visually, the fact that you can see the connections is super, super helpful. And just to know basically that you can also move them around, they color code and all that stuff. It's a very helpful tool, right? If you're having a hard time conceptualizing your database, stuff like this really helps. I will say this is a fairly simplistic database. There's 6 data tables that we're holding information in. Um, the connections are pretty logical and easy to follow. When you start getting into databases that get significantly more complex, the diagrams can also become really complex, and thus the ability to collapse them down. But regardless, it still is helpful, basically from the standpoint of being able to think about how things connect, how they work, and or why it works the way it does. It's kind of like, it's not really like looking inside the motor of a car, but sort of, you know, um, you know, it shows you the inner workings. Now, these diagrams, by the way, you can save the diagrams if you wish. You can also screenshot the diagrams if you wish. And any database that you're working with that pre-exists, you can do that with. So like if I wanted to do one of these other ones here, like let's say classic models, I would go here, I would reverse engineer, same steps. I'm just going to walk through the steps again so you guys can replicate it. I can choose which database I want to work with, and I'll choose classic models in this case. And the process is basically the same. And then it goes ahead and creates that document or image, if you will. And then once again, like what I would do, right? And this is me, that maybe not you, is I would try to arrange it so that I could see where all the connections go. And this is pretty good actually. And here's one that loops back. That's kind of interesting too. But see how this one's a little bit more complex, and it has mostly one-to-many relationships in it. I don't see any many-to-manys, but notice the order of them. But all those same highlights and color coding and all that stuff is still there, right? So very, very helpful, especially if you're working with a database you've never worked before, and you're trying to write queries for it, it is helpful to be able to examine the structure of something. But what's additionally helpful about that is when you're going to build something, you can look at what other people have done and go, oh, why did they do it like this? Okay, I think I might do it like that too. Or I hate how they did this. Maybe it should have been better done like this. And that's I think kind of a helpful way to look at it. Uh, so this is basically what we call an entity relationship diagram. So the entities, the tables and how they relate, is a good way to look at it. I have some other links here that I'm going to pull up. And this one here actually pulls up a document, and I'm going to zoom in. Oh, maybe even another click here. And I'm going to walk through this content here. And what this document is, these are lecture notes that Christian was using when he was teaching the class. And he does a really nice job of that. If you've ever taken a class with him, you know what I'm talking about. He always does that for his students. So like whatever he's like preaching to you that day, he's giving you the document with all that information, kind of like, lecture notes basically, so that you can study from them and think about it. So he did such a nice job at it. I decided to leave it here. There is some content here at the bottom of this that is based on SQL Server, not MySQL, although the concepts are still relevant. Okay. So let's just go through this document quick and hit some of the main points. And it says, database design is a process in creating proper structure of database tables, proper relationships between those tables, appropriate data constraints, and other structural components. So like, I think the first two are pretty intuitive, right? So like, okay, what stuff should go on the table? I think we've had some good examples. How should those tables connect? Same, right? I think we've had some good examples already. Data constraints is a different one though. So for example, if I was entering an order for a customer in the orders table, a data constraint must be that I have a customer in the customer table that relates to that order. Otherwise, who's ordering it? See what I mean? So like in order for you to place an order for a customer, first they got to be a customer, right? That's a thing. Other structural components, so like the data types, the capacity of the data, or things like an index, all of those things. All right, three well-known design types, right? And sometimes, and I gave you the example, like a doctor's office that has patient records on paper. And this is really kind of an interesting thought, because I've experienced this very precisely like this, is I used to go to this dentist that kept all the records on paper. And then a year or two ago, they're like, okay, we're doing it all on the computer now. So even when I like sign a form or I see my x-rays, it's all on the screen, right? However, none of my old stuff is transferred over because they're not going to go back for like, I don't know, 20 years of running a dentist's office and take every piece of paper and enter it into the database. They're just making a choice basically that, well, all right, well, we have this information, but we're not going to take the old stuff and put it in. Or maybe they don't have that much information and they've decided that we have this existing data and maybe it's on paper, right? Or maybe before we put it in a database, we were just putting it in a spreadsheet or a document or a text file or something else. And we have data, but we just need to turn it into a database because the way we have the data now doesn't really work for us. Right. And that's a very normal thing. So a lot of times people, before they build a database, might have a spreadsheet of information. So that's very common. So that's what they're trying to show here is like, you could be building something from existing data. And so if you have an existing data, what does that look like? Well, it could be a spreadsheet. And, if you are working with a spreadsheet, like I happen to have a couple open here, right? Oh, yeah, and that's horrible. Sorry. Because that has email addresses in it. Those are all fictitious, by the way, YouTube. If you have an existing spreadsheet with information in it, spreadsheets often have many tabs. So for example, I can have a spreadsheet that has many spreadsheets within it, and we call those tabs in the spreadsheet. I could also just have the information in a text file. That text file might just be plain text, or it might be tabular information like a CSV file or a JSON file or something like that. And then we're using that raw data to build the database, and in principle, hopefully be able to import it somehow directly. And that is somewhat of a possibility, but it's a bit of work, right? Sometimes the work is done manually. Other times we can take it like a spreadsheet and output it as a CSV file or some raw format like that, and then import it into the database. That is possible. Sometimes we have to write code to do that, and that's pretty normal too. So some weird thing like that, but the data that we have will help to dictate the design. Right. Another possibility is that we have a different database system, right? Like, and they're using examples like you might have a employee relationship database or a customer relationship management system in place, and I can extract data from that and then use that data to build a new database for some other purpose or some other goal, for functional purpose. So that's very common. They are not really saying here that, oh, what if you're starting with information on paper? That's a way to do it too. How's the data going to be entered? Manually, right? The old-fashioned way. And I think I've shared this story with you. Like one of my first jobs in IT, and this is working like right out of graduating from school and getting a job with like a IT temp service. I got a job at this publisher here in town, and my goal was to take all their let's call them fan letters or whatever, or reader letters, and put them all in a database, names, addresses, and what the letters said. And it was manual because people wrote letters by hand back then, and I would like type their name in, type their address in. If they provided other contact info, I'd type it in, and I'd type in the body of their message. And that way, the people that worked at the publisher would have this database of all the users that are into their magazine and could interact with them. And then when like a new magazine was coming out or something, they could like email them or whatever, or send them a piece of mail. Another approach is to design for a brand new system. You don't have data. You just have this thing that you're doing, and you're going to generate data, and you want to have a place to put it. Okay. So how are you going to get, well, here's the thing. How are you going to gather the data in the first place? Are you going to do it electronically? Are you going to do it manually? Are you going to have them fill out a piece of paper and have somebody type it in? That still happens a lot, right? Like a doctor's office is a good example. Here, fill out these forms, and then they take the paper, and then somebody types it all in, and hopefully they type it in correctly. Right. That's one approach, or it could also come from other systems potentially. But when you're building a database from scratch for a certain purpose, like let's say I'm a brand new doctor and I'm starting a new practice, and I know that I have to I have to get their, name, address, phone number, whatever, probably a medical history, maybe insurance information, whatever. And I might actually, like my dentist does now, is like when I fill out a form at my dentist, they just hand me an iPad and I do it on the iPad. And it's like, okay, great, right? I don't have to write on paper. And I know the data is going to be right. But you have to think about how that data all links together. Like, what information do I put in this table, or what information do I put in that table? And that's why, we look at the forms that people fill out or reports from other systems. We look at what the users of the system require. So, for example, the doctor's office might need insurance information from their clients in order to process insurance payments. So it's required that we have their insurance info or payment information. And there's always going to be different needs. Like every situation is going to dictate different information is needed. And then when you know what information is needed, then you create what we call data models. Like, okay, what information are we gathering? What does that look like? What particular attributes or fields are we building? First name, last name, address, city, state, etc. Right? And then we would convert that. In other words, we look at like what information that is, and then we determine what data types they are, how we connect the data together, and then we build a database. Now, this is a little bit more challenging because you got to conceptualize all this stuff from scratch, right? You're not following a model. However, um, there are templates, right? A great template is to look at a database that already exists, see how they do something, and just mimic it. That's okay. Or maybe you are really coming up with some brand new kind of concept, like how am I going to link this stuff all together? And you start from scratch and come up with something maybe completely new, right? All right, so that's another approach. Another aspect, and this is something that does happen in the database world, especially when we're upgrading from an older database system to a newer database system. We do this thing called migration. So, for example, web developers in particular, right? So, database migrations are really common in web. So, for example, I might build a website that has a database behind it, and then I'm like, well, you know what? I'm going to spin up a new website, right? I don't want to rebuild my database. So I'm going to migrate it to this new system. And what that means is they basically make a copy of it and adjust it. And that's called a migration, right? So that's possible. It is possible to do that, to just replicate a database and then retool it a little bit. Or maybe you have this kind of situation, and this is what we call, notice, migration, right? Kind of like duplicating it and adjusting it versus integration. Very common in the business world. It's like, okay, well, we have one database for our patients. We have another database for our insurance companies, another database for our x-ray results, another database for whatever, right? And wouldn't it be helpful if they were all together in one database? Yes, right? So another common approach is to take two or more database systems and their information and integrate them together into one database. And so that's an approach for building databases too. Now, when we do build a database, so we're going to work with the create database command today, and we'll work with the drop database and all that. But we're also going to be building tables as well. And what the point of this silly little table, talking about tables, is to explain some of the terminology that we use, right? And so notice that the term relation and table are often used interchangeably. And I'm going to take it a step further. Tables in the old days, when I first learned databases, we didn't call them tables, we called them files, rows and columns, but we called it a file, right? And think about that. If you're at the doctor's office and they have a bunch of files in the file cabinet, right? And you go, where's that? Well, it's in the file. There, it's filed over there, right? And is that really a table? No, but that's how the information is built up conceptually. So what they're trying to tell you here is a table, is also a relation. So it's relating to a piece of something identifiable, right? And we think about an entity basically. So, for example, a table might be for a customer or orders or parts or accounts or whatever. And then a table has rows and columns. Each column is an attribute. So, for example, last name is one of your attributes. First name is one of your attributes. Your student ID number is one of your attributes. We also think about that as a field in the database. So a column is kind of like a field and an attribute. These are synonymous. With a row, then we're looking at an individual record inside the database table. So one row in a table holds information about one record that is unique, right? And the tuple here, you guys will recognize this as Python terminology, right? A tuple being an immutable list, right? Or basically a piece of information that's married to another piece or pieces of information, all part of the same record, right? So table, column, and row, field or file, field, and record, and then relation, attribute, and tuple. My brain thinks about the first row and the last row. I really don't think in this terminology much in my brain, real frankly, but it is valid. Tables do have relations to other tables, right? So all relations are tables, but not all tables are relations, right? So it's a special aspect of table. So some of the terminology we throw around here too, right? And the definitions for all this stuff is below. So relation generally refers to a table or a connection to a table. We have a functional dependency. The value of one or more attributes determines the value of another. Okay. So for example, I'm trying to think of an example here. All right. Well, what about like if you lived in a city and state, right? If I lived in a certain city and that city only existed in one state, well, the state and the city are related, right? They're functionally dependent. Determinant is a column that determines other columns. So, for example, if I say order placed and it says true, that might affect the orders columns if there are such a things. We have candidate keys, primary keys, surrogate keys, and foreign keys. And the ones that we normally worry about the most are these two, right? A primary key must be unique, so you can never replicate it. A foreign key is one that links to a unique primary key in a different table, right? Now, look at these. These are kind of weird. The candidate key is a determinant that determines all the other columns in a relationship. This is, I'm going to call this a higher level concept that we're not really going to encounter much in this course, but it is possible to form these kind of connections. And then we have what we call the surrogate key. Notice this is an artificial column that is added to a table to serve as the primary key. And this is actually a very common practice. So for example, sometimes like, so for example, if I had a table of you guys as students, you would think that your student ID would be the primary key. But sometimes what this is telling you is that database designers will just create a junk column and just put a unique number in there that usually auto increments. And they make that the primary key because then it allows for other columns to sometimes replicate or be changed or whatever and not pollute like other information. So sometimes they create a fictional column to just for the sake of having a primary key, right? Usually when one is absent. Okay, so for a table to be a relation, the criteria of this definition must be met. Rows contain data about an entity, right? So like if I look at a customer table, one row refers to one customer who is an entity, right? Columns contain data about attributes of the entity. We talked about that already. So that entity has a first name, last name, address, phone number. All entries in a column are of the same kind. So if I have a last name column, that's only last names in there, right? Each column has a unique name. So I can't say name for last name and name for first name. Last name, first name. That's why we give them different names. The cells of the table hold a single value. That's true, but if you think of some of the data types that we sort of got introduced to, there are enumerations and sets which can hold multiple data points, but generally that's true. One single value in cell. The order of the columns is unimportant. So if I create a table and I put last name and first name at the far right end of the table, doesn't mean they're not valid and doesn't mean I can't run a query that puts them first in the output. So, and the reason they bring this up is sometimes you create a table and then later on you think of like, oh, maybe we should include a column for email address, that kind of thing after the fact. And so the order doesn't really matter. The order of the rows is also unimportant. That's kind of a weird thought too, because if each row contains information about one entity, it doesn't matter what order it's in. If I'm querying for it, it doesn't matter where in the table it is, as long as I can find it. One that is really important though, no two rows of a table can be identical. I'll give you an example. What if you had two people name the same thing, like John Smith, have the same birthday, live in the same town, maybe live at the same address, like every piece of information is the same. And the only thing that's different about them is their student ID number. That's pretty rare, but it does happen. So then that primary key or that ID number becomes the thing that makes it unique. But one way or the other, they are unique. And that is weird, but it's true. All right. We are going to get into this concept of normalization, but I'm going to bounce back here to look at this. But I want to really talk about these points in a separate fashion. So I'm going to bounce back over to the core shell now, and I want to talk about normalization a little bit, and I want to look first at the terms that go with it, and then we'll look at a sample of unnormalized data and how it gets normalized, which is a great precursor for doing our homework, and then we'll kind of circle back to that document. All right. So when we're looking at normalizing a database, and you know what? Let's do it like this. This should be kind of fun. And I'll use let's use Gemini for this. I don't know if I can pull up Gemini here. There it is. And I do this verbally. Please describe what normalization is for a database. I'm just going to we'll send that off, and let's see if it reads it back to us. All right. And so let's look at what it says as a result here. And yeah, I could have it read it back, but it basically says it's a systematic process of organizing data in a relational database. Its primary goals are: one, to reduce data redundancy. So for example, if I'm keeping patient information, do I really need to put their address on every record that they are involved with? No, we just need it once and to have it be correct. To improve data integrity, in other words, to make sure that the data is accurate, consistent, etc. And then to enhance data flexibility and maintainability, basically meaning by separating data into separate tables, we can make it a lot more flexible to query, extract a lot more information without using more space, that kind of thing. And then generally, when we normalize our information, this is one of the reasons they originally did this, by the way, is to increase the performance of queries in a database. The output here goes on to explain how these work. So we'll come back and double check this later, but we usually worry in database design to get up what we call third normal form, and it's a building process. So right, when we start, especially when we start from scratch, we have to think about, okay, what data are we collecting, how are we separating it into tables, how the tables connect, all that stuff, and then what might be redundant, what's our primary key going to be, and all that, right? And it's a building process. There are what we call higher level forms, right? And usually, and actually it goes beyond third normal form, but you'll notice that back in the old days we called that fourth, fifth, and sixth. Okay, so there are higher ones, and those are really challenging to achieve for a lot of database people, by the way. And notice what it says here when you get to those real high ones. Over normalizing can sometimes lead to an excessive number of tables and complex queries, which might negatively impact performance in certain scenarios. So usually for most database people, we try to reach third normal form as a general rule. All right. I think we're at a great spot right now to take a break. So let's do a 5-minute break, and we'll come back at about 6:41, 6:42. So I'll see you guys in a few minutes. All right, we're back from break, and now we're going to take a quick look at these normalization terms. And we saw that from the output of Gemini there momentarily. But basically, what we when we see these acronyms, by the way, this refers to first normal form, second normal form, third normal form, and usually we try to get it to about that level in a database. Okay, so in first normal form, and this applies basically to any table, right? So that's, so what does it apply to? All tables. And ultimately, what we're looking for is redundant information and want to eliminate it. So, for example, we wouldn't want to list, for example, all the information, let's say like a person's name, like multiple times, or their address or their city and state several times, or you don't want to have a first and last name column and a whole name column, perhaps, that kind of thing. So every separate piece of information should go into its own column and in its own table, and all tables have a primary key set. So one of the goals there is to make sure all the columns are unique and that we have a primary key. And the primary key is really the most important part, right? Because that's ultimately what makes every record unique. With second normal form, we look only at tables with what we call a composite primary key. And so, in other words, that the primary key might be a couple of fields working together. And so sometimes, for example, some people might use an ID number and a last name to form a primary key. So two pieces of information. And then it says for those tables, determine if the non-primary key columns depend on the whole composite primary key. So like, do we need to have two pieces of information making the key? I have found some circumstances when I was doing some database work where it made more sense to me to have a combo. I can't remember those off the top of my head, but there were a couple weird situations. A third normal form, we look at all tables, we look at non-primary key columns and make sure they're not dependent on another primary key column. Okay, those are pretty vague, real frankly. I think the description that we got from Gemini might actually be more helpful. So I pasted that into a Word document. And so let's take a look at it in this format here and see if that helps us. So in first normal form, all right, we eliminate repeating groups of data within individual tables, right? So no repeats. Each column contains atomic, meaning single indivisible values. So for example, if I had my first name and last name combined in one column, those are divisible. I can put last name in its own column and first name in its own column. If I took my phone number, I wouldn't want to split that into two columns. Okay, I could get people that would argue, no. You could have one column for area code and another column for the number. We don't think about it like that anymore, but there were database people that used to do that. Each record is unique and identified by a primary key. All right, so that's first normal form. Second normal form begins with, it must be in first normal form first. So you got to make sure this stuff is true before you can do second normal form. And then all non-key attributes, so columns that aren't part of the primary key, must be fully dependent on the entire primary key. And it says applies particularly to tables with composite primary keys made of multiple columns. So in other words, if I have, for example, two John Smiths in class, right? They each have their own ID number. Well, I need to differentiate them. Really, the only way that I can really differentiate them is with that primary key. This is what it's telling us. Or if I was using two or more columns together to form the primary key, maybe an ID number and a last name, something like that. The rest of the information is dependent on those being present. So the primary key has to be present in order for us to be able to get the second normal form. You guys granting that, whether the primary key is a single column or multiple columns. In third normal form, we must have already achieved second normal form to accomplish that. And then we start to do this. We eliminate transitive dependencies, meaning non-key attributes should not depend on other key attributes. All right. So in other words, does a person's address depend on the primary key? No, it doesn't, because I could be, for example, in a patient database, and then I move and I have a new address. It's not going to change my patient number. It's just my address changed, right? So it's not depending on that. So also, if I change, let's say I change my phone number, or let's say I change my address, doesn't mean I'm changing my phone number, right? Those are non-key attributes. So now keep in mind, tables can also have foreign keys, right? Right, that have to be attached to other tables. And this is a little bit deeper. All right. Okay, so notice the Boyce Codd normal format. It's a stricter version of third normal form. And it says a table in this format, if every determinant, an attribute or set of attributes that determines other attributes is a candidate key, they can uniquely identify a record. And I think this is really where you're looking at combinations of pieces of information to make them completely unique. This is going to be a much deeper ask, and it is stricter. Once again, there are fourth, fifth, and sixth normal forms, but most database people kind of cap it at third normal form. And right now we're going to go look at an example of this. So I think it'll make more sense looking at the example than listening to my verbal description of it, frankly. All right, so here I have a link that takes us to a spreadsheet. And I want you to notice that this spreadsheet has a bunch of tabs here at the bottom that shows the normal forms being applied. And we start with unnormalized information. Why is this unnormalized? All right, well, let's look at it. Well, it's an employee table. It does have an ID field. Okay. Are the IDs all unique? Well, they seem to be. And you notice that, I mean, it looks like maybe Christopher Christian entered a Jay Leno in the table here too. So then we have a name column. Okay, I see a problem there right away because last name and first name are together. Okay, that's problematic. Then I see date of birth. All right, that's going to be a date. And age. Okay, let's talk about that. Can't the age be mathematically determined by the date of birth? So the age is accurate when I enter it in, but next year it won't be if it's hard coded. So I might argue we might not need that column, right? Because this is really determined by looking at this and today's date. That's how we know the age. So this is that one example. Like this depends on this to be correct, and if we're hard coding it, it's not going to be correct soon. Right? Then we have a department, and notice that's just kind of written out verbally. I could think of different ways to do that. We have titles that could probably be done differently. Then we have pay codes. All right, salary, and I'm not sure what HR means. Hourly, probably. And then we have a description of, I'm assuming, the title. Right. So once again, this seems to be dependent on that to me, right? All right. So this is raw information. This is not unusual. So even though there's a ID field, we have information dumped into a spreadsheet, and it's not optimal. This is unnormalized. All right. Let's go to first normal form, right? And what did we do to change the table here? Only one thing happened. We set a primary key. So the first column was declared as the primary key. And when you do that in a database, of course, that makes each one of these forced to be unique. Thankfully, they are, so we didn't have to delete anything, right? But all these numbers are unique. All right. Nothing else changed. Everything else is the same. Moving to second normal form. Right now, notice what happens in second normal form. We are now, we have our primary key. We are taking these weird pieces of information like the department ID, the title of the employee, and their pay grade. And instead of listing it here verbally, now we just have a number that relates to the primary key. So if I look at department ID in the department table, I can figure out they work for HR. Or if I look at 6, they work in the news department, right? But what's the advantage here? Well, now I'm not taking all this text to store it here. I'm just storing one character or one number. A lot more efficient, right? But it still points me to that information because we're going to form a relationship from here. And notice that switched to a foreign key. So now this primary key here becomes a foreign key here. It can only exist here if it exists here as a primary key. And therefore we can extract that information. Same is true with the title and the pay grade, right? And notice, the pay, salary, hour, and I'm not sure what that one means. And then we also have another connection, and I don't know if you see this, and this one's marked as third normal form. So second normal form is splitting these pieces of information as foreign keys out to these 3 tables. Third normal form, and I don't know if they do it over there too. I guess it's on both, whatever. But third normal form takes the description ID, right? They come up with this unique value. Why? Just to make each record unique. And then we're linking it to the foreign key of the employee ID. So this is linking back here, and then it's giving us the description of the employee. So we're not taking all of this text here and adding it to each one of the employee records, but how are we linking? We're linking through the employee ID number. So this links back here. This primary key links to that one here, and then I can pull that record. Now, despite having the foreign key, it does have a primary key of its own. What does this mean? Nothing. It just makes the records unique. And if you notice, same is true here, same is true here. And that's not an unusual database thing. The other thing that you could do, and I don't know if it, okay, so they do break it down here, third normal form, and it's the piece that I was kind of pointing out. Notice when we go from second to third normal form in the primary employee table, now we're splitting first and last name, and we remove the age column, and we just have date of birth, because I can calculate the age based on the date of birth. So if I ran a query and wanted what's their age, I would just do a formula that takes, today's date minus their date of birth, and boom, you got it. So that's kind of a good example. Now, the homework that goes with this unit is basically doing something similar to this. And I just want to make sure that everybody's clear on like the procedures of it before we dig into the actually doing the homework of it. Now, a lot of concepts we threw at you here today, and I want you to think about this really carefully, because what might be a really good example is when we look at, let's say we look at My Guitar Shop, and I'm just going to do a use statement here just so it attaches, and then we do that reverse engineer again, and I'm just going to do it quickly. My Guitar Shop, build it, and finish. And then once again, you can move all this stuff around as you see fit, right? Customers, addresses, products, administrators doesn't really attach, categories, order items, orders, etc. Okay. Now, noticing how these tables are put together, we're assuming, all right, so there's a big assumption that this is a well-built database. Um, but you could probably argue against it if you really want. Are there ways that we could raise the normalization level of this by looking at certain things? And real frankly, right, when we're looking at, let's just look at the customer table, for example. I'm going to just make that a little bigger like that. All right, the first and last name are split apart. We have their password stored. That's a little weird. I might argue that a password has no place in the customer table. Um, so that might be one might break out. I might have like a separate table for passwords. And these are the kind of things you look for as a database person, right? I don't want, let's say, like if somebody has access to this data, I don't want them able to see the customer's password. Or granted, it might be encrypted or whatever, but that's a thing. Billing address, shipping address, are they an active customer? Remember, we had that one too. And then you can see that we have a separate thing for addresses because sometimes customers have multiple addresses, that's certainly an issue I had when I was running my business operations. And I guess when I worked for Gateway, I could have packages shipped to Gateway too, if I wanted, but these are the kind of things that we look at. But we assume all these databases that we're given and we're working with are normalized, at least to, second or third normal form. What you do discover, though, is that database admins do miss certain things like that, and it takes really experienced, knowledgeable ones to build databases that are well normalized and operate efficiently. One of the reasons why we do split information, and going back to that info that we pulled down, is to kind of have this balance between like efficiently storing the information and also having the queries run effectively. If I break the information out into many, many different tables, like more than what I have here, the queries would be a lot harder to write. They might not make as much sense. They might take longer to execute because it's got to traverse more connections to extract the data. So those are all heavy considerations in this design aspect. All right, once again, I'm going to close these and it'll ask me to save and I won't. And now I think what we'll do is I'm going to cap this video here and we'll do a little bit of talking about the homework and then we'll record a separate video